Hello and welcome back to A Slice of Physics. We have been talking about light as waves and we have analyzed the wave properties of light. Now it's time to look at the ray model of light. In the ray model, we treat light as something that moves in a straight line, almost as if it was a bundle of particles. So why do we need another model? Well, we've mentioned that the wave model and things like diffraction and interference become noticeable only when the openings are comparable to the wavelength of light. The wavelength of visible light is half a micrometer, which is about 1/100th the width of a strand of human hair. So in a lot of our practical observations, we do see sharp shadows. We don't see interference fringes, and the ray model of light is very useful in understanding those observations. And it also helps us understand things like reflection and refraction, which are the topics we're going to explore with the ray model of light. So first, I'll introduce what the ray model of light is. Then I'll talk about how shadows are cast based on if the light emitting object is a point source or if it's an extended source. We will look at what the law of reflection is, and we will consider how images are formed in mirrors. Okay, in the ray model of light, if I have a light source that's a point light source, a tiny light source, a laser pointer is a good example of a point light source. Stars in our night sky are great examples of point sources because even though stars in physical size are huge, they are so far away that our eyes cannot resolve them, so we can treat them as point sources. So a point source sends rays of light. As long as the point source is emitting object, it can send rays of light in all directions. And if I have an extended source like a light bulb that I'm standing close to and looking at, then every point on the light source will act like a point source and can send rays of light in all directions. So I can get rays in all directions from every point on this light bulb. So the key thing to remember with the ray model is that rays of light travel in straight lines. So once the ray of light leaves the light emitting object, it continues on in a straight line, and two rays don't interact with each other. So already we're contradicting some of the things we said in the wave nature of light. That's how these two models are. They are not consistent with each other. Waves spread out, rays of light travel in straight lines. Waves, when they meet at a point, will interfere with each other. Rays of light do not interfere with each other. And then third thing we said is there is no shortage of rays. So if I have a light source, it can have pretty much infinite rays going in every direction that we want. So this model is useful in describing things like shadows. So if I have a pencil here that I hold in front of a small light source, a point light source, and I have a screen over here, what we see on the screen is just a bigger, I'm going to show a 3D representation of it, even though the shadow is going to be 2D, but I will see a bigger version of that pencil like that. So here's my shadow of the pencil when there is a point source of light. Well, how do we explain this? We said that a point source will send rays of light in all directions, so there will be one ray of light that just skims the top end of this pencil and goes and hits the screen over here, and then there are rays of light above that that'll hit the screen directly. So this part of the screen has light that's hitting it. And similarly, there's a ray of light that will skim the bottom tip of this pencil and go hit the screen. And then there are rays of light below that that'll hit the screen. So the screen will have light over here. But the rays of light that are going straight through here are obstructed by the pencil. Oh, one thing I forgot to mention when I mentioned the ray model of light is they travel in a straight line until they are obstructed by an object that absorbs it, reflects it, or scatters it. Absorption is where the object just uses up that light to heat itself up. Reflection is when the light bounces off. We'll talk a little bit more about that coming up soon. And then scattering is a process of absorption and re-emission where the object temporarily absorbs the light and then re-emits it in some random direction. And then the fourth thing that can happen that we'll talk about in a future video is refraction, where the ray of light will bend as it passes from one medium to another. But back to our shadow. So in this case, these are straight lines. So by geometry, if I take a center line over here, this angle is the same whether I go up to the pencil or I go up to the screen. So this angle is what it is. And so there's a relationship between the height of the pencil, or half the height here from the center to the top tip, and the height of the shadow. Let me call that h prime. And these two are related based on the distance between the light emitting source and the object. So let me call that s, and the distance to the screen, let me call that S prime. And because theta is the same whether I take this small triangle or if I take this big triangle, you get the relationship that H prime over H equals S prime over S. So rearranging that, I'll get H prime equals S prime over S times H, which tells us that the size of the shadow is related to the size of the object, the distance of the object from the light emitting source, and the distance of the screen from the light emitting source. And then in the same situation, if I had, instead of a point source, if I had an extended source, so let's say I have a flashlight with a certain size that's sending light from it, and then I have a pencil in front of it and a screen behind. So now my shadow is not going to be so sharp. And the reason for that is, if you think about these two lines here, in between here is going to be a dark shadow because there are no rays of light that will be able to penetrate and enter this region. But then there's going to be a portion of the screen which will have a faint shadow. So it'll go from the dark shadow to complete brightness in a graduated manner because I have this line here. And while the light from the very bottom of this light source cannot reach this portion of the screen, the light from the top part of the light source will reach this portion, so it'll be partially illuminated. So it'll be a faint shadow that'll get fainter as you go up, and similarly there's going to be a shadow at the bottom which will be a faint shadow that gets brighter as you go down, and then below that it's going to be bright. So there's going to be light hitting this part of the screen and this part of the screen from the entire light source, so it'll be bright. Okay, so now the shadow will be a fuzzy shadow with a fuzzy outline. The only difference between when I see a sharp shadow here and a fuzzy shadow is that the light source is a point source versus an extended light source over here. All right, let's now move on to talking about reflection, which is a property of mirrors. So when I have a ray of light hitting a mirror, it bounces off and reflects. So I show the direction of the ray like that. And the law of reflection simply states that the angle of incidence equals the angle of reflection. So light always bounces off in this symmetric fashion. And these angles are defined based on the normal to the reflecting surface. So this is a mirror, so I'm going to show it like this. And there is a normal to it. Normal in physics, remember, is perpendicular line. And the angle of incidence would be this. Let's call that theta I. Angle of reflection will be this. Let's call that theta R. So the law of reflection states that theta I equals theta R. As a last step, I'm going to talk about image formation in plane mirrors. So once again, I have a mirror here that's flat, and I have an object here. And now let me take a point object, just a very small point object that's sitting in front of the mirror, and I want to see what the reflection of this in the mirror would look like. So this point source is going to be sending rays of light in all directions, as we said before, and some of those rays are going to hit the mirror. So one of those rays that'll hit the mirror is the one that goes straight like this, and you know from just our previous discussion that the angle of incidence for that with the normal is 0, which means the angle of reflection is also going to be 0, which means this ray of light just simply turns back on itself. And then I would have a ray of light that goes and hits the mirror here. The angle of incidence for it is that. The angle of reflection would also be equal to the angle of incidence. And then there would be another point that'll hit the mirror, let's say over here. It's got a smaller angle of incidence, smaller angle of reflection. So I've taken 3 rays here. There are many, many more, and you can draw them all out, and they will still be consistent with our discussion here. The question is, if you are looking at it, and let me just take one more ray here just to illustrate the example that I'm talking about. So there could be a ray that hits the mirror somewhere in between, and it'll have a reflection like that. So if you're sitting here and looking at it with a giant eye, what will you see? Well, you see rays of light that are diverging from each other. These rays of light are getting farther and farther away from each other as they go after the reflection. So they're spreading out. Well, when you extend them back into the mirror, something interesting happens. They all seem to be coming from a single point. And even this other ray that was going back on itself will also intersect at the same point. So all of these reflected rays intersect at a single point behind the mirror. And if you are here looking at these rays of light with your eye, they appear to you to be coming from a point that's behind the mirror that's sending these rays of light. So these are dotted lines because there is no real light here. They just appear to be coming from that point. All the light is on the left side of this mirror that is coming from the object or being bounced off. So because of this appearance, we will see the image of this object behind the mirror over here. So see the object here. And since the object is not really behind the mirror, what we're seeing is an image of the object. And once again, based on geometry, if you work this out, this normal here can be extended behind the mirror. This angle of incidence equals this angle of reflection. And based on just how intersecting lines behave, this angle of reflection is the same here. So all of these angles are the same. So what ends up happening is that the object distance from the mirror S and the image distance behind the mirror S prime end up being equal to each other based on the law of reflection. Image of the object at a distance behind the mirror as the object is in front of the mirror. And by the way, if this object was not a point source, but again, an extended source like a pencil, so I'm going to take another pencil here. Every point from this pencil will be sending rays of light on the mirror. Every one of those points will reflect off the mirror, and they will seem to be appearing from a point behind the mirror. And so when you see the image of this pencil, it'll appear to be behind the mirror at the same distance as the pencil is in front of the mirror. You can simply see that for yourself by taking every single point along this pencil and doing the ray tracing like we did above, and you'll see that the image of this point will appear here, the image of this point will appear here, the image of this point will appear here, and so on. And so the entire image is constructed based on the series of points behind the mirror. All right. So in this video, we looked at what the ray model of light is. We saw that it's useful to explain lots of day-to-day observations. So we adopt that model as well for light, and we use that to figure out how shadows work and how reflection works. We saw that light rays travel according to this model in straight lines and don't interact with each other. We saw that point sources of light cast sharp shadows, whereas extended sources of light, like a flashbulb, will cast a diffuse shadow. And we saw that the law of reflection shows us that the angle of incidence equals the angle of reflection, and these angles are measured with respect to the normal of the reflecting surface, the perpendicular line to the surface. And we saw how all of this leads to the image formation behind a plane mirror. Thank you.